Hello, so today we'll be learning limits. The first thing to know about limits is limit notation. The general notation is going to be limit as x approaches a of f of x is equal to L. And this is best understood through an example. So here we have an example of a limit. It's the limit as x approaches 4, it's the square root of x. So a is always going to be a constant. In this case, it's 4. And the f of x is always going to be a function. But what exactly is a limit asking? Well, here we have the rough graph of y equals root x. And the limit is basically asking what the square root of x is equal to as x approaches 4. So in order to solve this limit, we're going to have to see what x is equal to as it approaches 4 from both the left side and the right side. So another helpful notation to know is the limit as x approaches 4 minus the square root of x. And this is essentially what the square root of x is equal to as we get closer to 4 from the left side. Similarly, the limit as x approaches 4 plus the square root of x. This notation is going to tell us what the function is equal to as x approaches 4 from the right side. And so in this case, they're both equal to 2. And so if both the left-hand limit and the right-hand limit are approaching 2, that means that the limit of the function overall is equal to 2. So the first limit strategy we're going to go over is called direct substitution. All you have to do with direct substitution is look at the value that x approaches, which in this case is 2, and plug it into the function for x. So you should get 3 times 2 squared minus 2 times 2 plus 5 over 4 times 2 minus 7. And if you do the math and work it all out, you should get 13. This is by far the easiest limit method. Now, unfortunately, direct substitution doesn't always work out. In this case, we can see that if we plug in 5, the top is going to be 0 and the bottom of the fraction is also going to be 0, which doesn't exist. So what we have to do is we can actually factor. So we can factor a 2 out of the denominator. So we get limit x approaches 5, 2 times x minus 5. And we can factor the bottom to be x plus 5 and x minus 5. And what that gives us is we're able to cancel out the x minus 5. So we get limit x approaches 5 is equal to 2 over x plus 5. And at this point, we can actually do direct substitution, and we would get 2 over 10 or 1/5. So by using factoring, that would be our answer to the limit. So for this problem, we can see that direct substitution isn't going to work because you'll get 0 over 0. And because we have a radical, the strategy we're going to use is multiplying both the denominator and the numerator by the radical conjugate. So in order to find the radical conjugate, if you're given a plus b, the radical conjugate will be a minus b. So you can see that there's simply a sign change in the middle. So here, because we start with root 1 minus x minus 3, the radical conjugate of that will be root 1 minus x plus 3. And you have to multiply this to the top and the bottom. Once you multiply that out, you should get limit x approaches negative 8 of 1 minus x minus 9 over x plus 8. You multiply that by the radical conjugate, so root 1 minus x plus 3. And the top here can actually simplify to limit x approaches negative 8, negative x plus 8 over x plus 8, and root 1 minus x plus 3. And here you can see that the x plus 8s can cancel out, which leaves you with negative 1 over root 1 minus x plus 3. What we do from here is we can actually use direct substitution and plug in negative 8 for x, which will give us the answer, which is negative 1 over 6. So here are the general rules for evaluating limits at infinity. So if you look at the degrees of the numerator and the denominator, and the degree of the numerator is greater than that of the denominator, then that means that you know that the limit is going to either positive infinity or negative infinity. In order to determine whether it's positive or negative, you're going to have to look at the signs of that equation. Then if you look at if the degrees are equal, then you have to compare the ratio of the leading coefficients. And if the degree of the numerator is less than the degree of the denominator, then you know that the limit to infinity is going to equal 0. So let's look at a couple of practice problems. So the next practice problem that we're going to look at is one in which the degree of the numerator is greater than the degree of the denominator. So that means we know that it's either going to be going to positive or negative infinity. And the way we tell the degrees is that this has an x cubed, whereas the bottom only has an x, which means that we know that the numerator has a greater degree. So what you would do here is you would only look at the terms with the greatest degree. So in the top, that would be 2x cubed, and in the bottom, that would be minus 5x. And when we simplify this, we can cancel an x from both sides. So we get 2x squared over negative 5. And so we can see that if we do direct substitution and we're going to plug in infinity, this is going to approach infinity, but because it has a negative on the denominator, it's going to be approaching negative infinity. So the answer to this would be negative infinity. So in this next example, we can see that the degrees of the numerator and the denominator are the same because they both have something raised to the x squared, which is their greatest degree. That means we only have to pay attention to these terms. So you look at 3x squared over minus 6x squared. Notice that you can cancel the 2x squared. So you're simply left with 3 over negative 6, which simplifies to negative 1/2. So that would be your answer. So in this next example, the greatest degree in the numerator is going to be this 5x squared, whereas the greatest degree in the denominator is the x cubed. And because the denominator has a greater degree than the numerator, we already know that this limit is going to be equal to 0. Alright, so this is a special case of limit because when you plug in 5 for direct substitution, you'll actually get negative 2 over 0. And so whenever you have any constant over 0, what you're going to have to, well, this actually goes to infinity or negative infinity. So what you have to do is you have to test both sides of the limit. So what I mean by that is we'll start by testing limit x approaches 5 minus. So this is the left-hand side of the limit. What you get when you do that limit is you get negative 2 over 0 minus, because you're taking 5 minus, which is slightly less than 5, subtracting it by 5, so you're getting 0 minus. And this actually goes to infinity, because something slightly less than 0 is going to be negative. So if you have a negative over a negative, that's going to give you infinity. Then after getting the left-hand portion of the limit, you'll get the right-hand portion of the limit. So it's the limit as x approaches 5 plus of 3 minus x over x minus 5. What you get for this one is negative 2 over 0 plus. And so here you have a negative number over a positive number, which means that this limit is actually equal to negative infinity. And because the left-hand limit and the right-hand limit are equal to two different things, we actually say that this limit is dne or does not exist. If the left-hand limit and the right-hand limit were equal to each other, then that would be the solution to the limit above. So one application of limits that you'll be tested on is using limits to find the removable discontinuity, the vertical asymptote, and a horizontal asymptote of a function. So in order to find the removable discontinuity, you're going to have to factor the equation, and whatever it can cancel out will give you the removable discontinuity. In order to find the vertical asymptote, you take the limit as x approaches a certain constant, either from the right or left-hand side, and if that is equal to plus or minus infinity, then that means you have a vertical asymptote there. In order to find the horizontal asymptote, you take the limit of the function as x approaches positive or minus infinity, and if that gives you a constant, then that's the horizontal asymptote of that function. Okay, so let's say we're given the function x minus 3 over x squared minus 2x minus 3. The first thing you do if you want to find a removable discontinuity is to factor. So you get x minus 3 over x minus 3 times x plus 1. Notice that you can cancel an x minus 3 from both sides, the top and the bottom. This means that x minus 3 is going to be a removable discontinuity. So your removable discontinuity is going to be at x equals 3. And the way you can confirm this is if you check the limit as x approaches 3 f of x, it should be equal to 1/4. But if you plug 3 into the equation, so if you get f of 3, that should be undefined. So that's what explains why there's a whole or a removable discontinuity in this equation. So next, we're going to solve for the vertical asymptote. We can see that when limit x approaches -1 plus f of x minus 3 over x squared minus 2x minus 3, remember that's equal to 1 over x plus 1 because the x minus 3's cancel out up here. If you plug this in, you're ultimately going to get infinity. So because it goes to infinity at limit x approaches -1 plus, we say that there is a vertical asymptote at x equals -1. And the reason why I knew to choose the value -1 is because usually vertical asymptotes occur when the denominator of the function is equal to 0. So if you look up here, because we have an x plus 1, if we were to plug in a -1, then this would cause the denominator to be overall equal to 0. Next, in order to solve the horizontal asymptote, we're going to take the limit as x goes to infinity of the original function, which is x minus 3 over x squared minus 2x minus 3. And because you know that the denominator has a higher degree than the numerator, you know that this limit is going to be equal to 0. So what we say is that the function has a horizontal asymptote when y is equal to 0.